Okay, so I will start now. So, very good evening, everyone, and uh, welcome to the problem solving session for coordination chemistry, which is taken by Professor Devasisri from IT Kharagpur, and myself Satya Prakash Yadav, a PMRF scholar from August 2020 years to now, and I'm working with Professor Satish Patel from Solid State and Structure Chemistry Unit, Indian Institute of Science, Bangalore. So about the course, basically in week one, we introduce you people to the coordination complexes and how they are different from the double salt. And then we went to the Werner theory, and then finally we classify the ligand in three parts. In week two, we basically discuss in detail about the nomenclature of the coordination complexes. In week three, we discussed about the coordination number from coordination number 3 to coordination number 2. What are the possible geometry for the complexes and their example. In week four, we basically discussed about the isomerism. So in that we discuss structural isomerism and stereoisomerism, and little bit about the coordination equilibria, about the stepwise formation constant and overall formation constant, and what is the Irwin-Lewis series. In from week five, we started discussing about the bonding in complexes. We discussed in detail about the valence bond theory, why it is called valence bond theory, and little bit about the crystal field theory, why it is called crystal field theory, and how they are helpful to describe the property of the coordination complexes. In week six, we discuss a special kind of effect in coordination complex, which is John Taylor distortion. So we discuss about the John Taylor theorem and John Taylor distortion, and about the spin crossover, how the low spin, high spin equilibria happen, and what are the different kind of DN configuration which show the spin crossover phenomena, and other nature of ligand, nature of metal. From week 7, we discussed about the color and optical spectra of organic uh, color and optical spectra of the coordination complexes, and we discussed all the thing through the crystal field theory. And in BK, we discussed about the Argel and Tanage-Suvanota diagram. So Argel diagram is basically for the high spin complex, and Tanabe-Suvanto diagram is for the low spin complex. And in week 9, we discussed about the application of crystal field theory, and basically in the hydration of 3D series, which is in the +2 oxidation state, and the size of the metal ion in low spin and high spin complexes. And then we discussed about the spinels. What is spinel, and how much of octahedral and tetrahedral words are occupied, and how many of octahedral and tetrahedral words are present in that. And in week 10, basically, we discuss about the magnetochemistry. We discuss about in detail about the magnetic property of the coordination complexes, and little bit about the ligand field theory, basically in the sigma orbital. So in week 11, we basically going to discuss about the pi orbital, and through which we will try to solve the spectrochemical series. Why pi accepting pi accepting ligand are the strong field ligand, while pi donor is the weak field ligand. And we discussed about the reaction mechanism 1 and 2 and 3. So what are these reaction mechanism 1 and 2 and 3? We will see in the problem solving session. Okay, so I will not give any brief introduction to speak. So I will directly go to the problem solving session, and then we basically discuss all the concept through the uh, this one. So first question is, like in a octahedral configuration, total how many p orbital available in the system? So the option A is 10, option B is 12, option C is 6, and option D is 18. So I will wait for 1 minute. Once you will answer, then I will explain what is the exact answer for this question. Can you write in chat box what is the answer for question number 1? D18. That is incorrect. The correct answer is not D. Okay, so let me tell you what is the correct answer for this octahedral configuration. So now we have first in octahedral we have number of ligand is 6. Each ligand has 3 p orbital. Now we have 6 px, py, pz. Okay, so total we have 80 p orbital. Up if we suppose that sigma bond fall along the x-axis direction, so your py and pz will be utilized for the pi bonding. So the total number of p orbital available for the pi bonding is 6 multiplied by 2 orbital py and pz are available for the uh, pi bonding, so that is 12. So the correct answer is 12. So I will just briefly draw how it's look like. So it will be like this. We have metal. Okay. So we have two perpendicular orbital, p orbital in every place. Like this. So each ligand has two p orbital to form pi bonding. That correct answer is 2. So actually it will be not like this, it will be like this. So it's a 3D image. If you draw, it will look like this. Okay, so we have total 12 p orbital available in the system for the pi bundle. Okay, so we have to write for the pi bundle. Among all four triply generated irreducible representation, pi bond far between. This is pi bond far between which orbital? T1g, T1u, T2g, or T2u. I will wait for 1 minute. You people can think an answer, then I will explain. C. Okay, T2G. Anyone else who has different answer than T2G? B. T1U. Okay. Okay. Now let me explain what is the correct answer and how we know that. So now first we will see what are the orbital available on the metal. On metal we have T2G, we have EG. This is from metal, and then after that we have uh, uh, A1G, and then we have T1U. So this is 3D. Suppose we are taking this is 4S and this is 4P. Right? This is available on the metal in octahedral geometry. Right? Now come to the uh, ligand. On ligand we have uh, EG, we have A1G, and we have T1U. This is for the sigma bonding. Once we get the reducible representation, you will see that EG, A1 and T1U will form the sigma bonding with the metal bond. Now, what is the reducible representation for pi? So, if we take the linear combination of the ligand orbital and find the what are the possible reducible representation is. So we have T1G, we have T2G, we have T1U, and we have T2U. Now if we see on the metal, we have T2G, EG, A1G, and T1U. Now your on metal your EG, A1G, and T1U are utilized for the sigma bonding, for the sigma bonding. So now what is remain? You have only T2G remain on the metal, right? So if we see that pi symmetry, we have T1G, T2G, T1U, and T2U. The answer can be T1U also, but the T1U orbital of the metal is already utilized in the sigma bonding. So only T2G is remain, which will form the pi bonding uh, uh, for the this complexes. So T2G is the correct answer for the uh, this question. Among all four triply generated irreducible representation, the pi bond formed between T2G orbital of the metal and the T2G orbital of the ligand present. This all the four which is present in the irreducible representation. Only T2G will be forming the pi bonding uh, between the your metal and ligand. Okay, I think now it will be clear for Rajendra sir, right? Why the T2G is the correct answer for the uh, this uh, answer for this question. Okay, and other thing I just wanted to discuss here, why like there are ligand, we have the pi donor and we have pi acceptor, pi acceptor. So now if I ask a subsequent question here, which one will give a, which one will be a, pi acceptor will be a stronger field ligand or pi donor will be the stronger field ligand? If I ask this question here, what will be the your answer? Pi donor will be the stronger field ligand or pi acceptor will be the stronger field ligand? Any answer? Can you just write in chat box that whether pi donor or pi acceptor will give a higher CFSE value? Are if I ask, which one will give the higher CFSE value? Anyone? Okay, so let me explain. So first I will just draw sigma complex. What are the orbital present for the complex? We have T2G and we have EG star. This is once we form the sigma and this is your delta. Now if you have a pi donor a ligand which has pi symmetry. So what are that filled pi orbital energy? So the filled pi orbital energy will be somewhere close to the T2G or somewhere little bit lower to the T2G orbital. So this is the T2G from ligand. Now what will happen? Again bonding and anti-bonding orbital will form, right? And here you have your EG star, right? So this is your T2G, this is T2G star, and now this is EG star, right? So previously your delta 0 is this, now delta 0 will be, now because this is filled already, this is filled already, so this will also filled from the pi electron from the your ligand. So the actual delta 0, this is delta 0 dash, so delta 0 dash will be lesser than delta 0. So a pi donor will be the weaker ligand compared to the just sigma donor. Now what happens if we take the case of the um, pi acceptor? So we have here this one, we have the T2G and this is EG star for the sigma complex, for the sigma complex. Now this is the pi acceptor, so it will be having there are either it has a pi star antibonding orbital or sigma star antibonding orbital. So it will be It will be higher in the energy because the antibonding are orbital, and it will be the empty. So this is a T2G from ligand. Now once it will form a this one bonding and antibonding, what will happen? This will go down. So what will happen? Previously your delta was this, now your delta will be this. So this is your delta dash. So basically your delta dash will always greater than delta 0. So that's why your pi acceptor ligand are basically more stronger compared to pi donor and sigma. Okay. Now let's go to the next question. The reaction of NiCO4 with ligand L, where L is PME3 or POME3, in NiCO3L. The reaction is what? It is a associative, or interchange IA, interchange associative, interchange dissociative. Okay, anyone else? Can you people tell what is the reason why you are saying that it will be dissociative and dissociative only? Why not it will be associative and interchange or interchange D? Because associative, I think most probable if I see, because anyway from 4 to 5 it can easily go, right? 4 we have, 5 we have a trigonal pyramid and square pyramidal. Can you tell me what is the actual reason why you people are saying that it is dissociative? If you have seen, they are basically your square planar complexes. It will go through SQ square bipyramidal or trigonal pyramidal. Because the associative involves 7 coordination intermediate. No, that is for octahedral case, not for tetrahedral. NiCO4 is tetrahedral, right? NiCO4 is tetrahedral. It is not octahedral. It will not go to the coordination number 7. It will go to the, if it is associative, it will go to the coordination number 5, not coordination number 7. Any other explanation? Do you people have any other explanation? Okay, so the correct answer is you are right. It is dissociative. What is the reason? First, NiCO4 is tetrahedral. Second thing is that this, what is the ligand? Ligand is PME3, is a bulky ligand. So steric factor is the main reason why it will be dissociative, not associative. Because PME3 or POME3 is a bulky ligand. So it cannot attack to the tetrahedral and form a 5-membered intermediates. Okay. So now I will go to the question number 4. Which is the HOMO of the CO molecule? S star 2s, S2px, S2px, P2px, P2py, P star 2px, P star 2py. Can anyone tell what is the answer for this question? Okay, no problem. If you have no idea. Rajendra sir, you have any idea? Okay, no problem. So let's see. This is the atomic orbital of carbon, which has 2s, 2px1, 2py1, and 2pz. This is the atomic orbital of the oxygen, which has 2s, 2px, 2py, 2pz. Now, in this case, this is just a representation. A representation. It's not the actual energy, because actually atomic orbital of the oxygen and atomic orbital of oxygen will not be at same energy level, because both are different. Uh, mm, both are different atomic. They have different atomic number. Their energy will be different. But this is the just representation which will be there. So we have 2s orbital, 2s orbital. So it will form sigma 2s, sigma star 2s. Now we have this 2px, 2py, 2pz we have. So it will form pi 2py, 2pz, which is lower than the sigma 2px. So 3 pi orbital is there. One will form the sigma and two will form pi bonding. Right? So your sigma 2px is basically the highest occupied molecular orbital, because it has carbon has so 1s2 is not written here. Carbon has 6 electron, 1s2, 2s2 and 2p2. Oxygen has 1s2, 2s2 and 2p4. Now if you fill 2s sigma 2s star 4 and then 8, and then last two will fill in the sigma 2px. So this is the highest occupied molecular orbital. Now people usually plot other way also, like I will just plot one more way how this sigma like cu orbital looks like. Just give me a second. Okay. Yeah. So how, well, like we have cu and we have 2s. This is carbon and this is oxygen. We have O here and 3. Now what basically they found, say that this is the first orbital. Then we have P sigma. P sigma, P sigma, okay. Okay. Then we have another. Then we have two more. Then here we have one S. And then we have P pi. And then we have so. So this we say that this is S sigma, this is P sigma, and this is P pi. Then we say that this is S sigma star, we have P pi star, and then we have P sigma star. But because this is mixing, so this we say that this is SP sigma, This is PS sigma, and this is P pi, and this is SP sigma star. So which is the your HOMO of the uh, uh, HOMO of the CO. So if you see, your HOMO is basically localized on the carbon, not on the oxygen. That is the another way to see if we see the actual energy diagram. If we consider a carbon and oxygen. Okay. So now I will go to among the following, which is not a pi acceptor ligand. Yeah, this correct answer is S to sigma to px. Sigma means S to px. Okay, that is the correct answer for this question. Okay, yeah. So here there is a like what can I say? Hmm, okay, among the following, which is not a pi sector ligand. Hmm, anyone else has okay. Rupali ma'am has D and this C. Yes, okay. Okay. Option C, option. Okay, I'm confused. Like, what is the answer you have given for five among the following, which is not a pi acceptor ligand? Actually, this not you cancel it. Now you tell me. Yes. Now you tell me what is the answer because this is not the correct question if we are writing. Oh no, I think it's correct. Yeah. Correct. So this. Huh. Mhm. Hmm. Will tell you. Will tell you. Okay, but C is not the correct answer. Can anyone guess any other answer? Because C is not the correct answer for this among the following, which is not a pi accepted ligand. Previously, Rupali ma'am, you write D, right? So D is the correct answer. Now I will tell you why D is the correct answer. Okay. Now let's take the first example. So sorry, we saw that pi acceptor will increase the CFSE value, right? Now the question: what are the different types of pi bonding available? Right. So the first one is d pi p pi. Second one is d pi d pi. Third one is d pi pi star. Fourth one is d pi and sigma star. Right. So now question is here. Now the question is here. If you want to make a like a pi bonding, so you have to have a matching symmetry orbital. So the matching symmetry orbital for the pi bonding, it can be p pi of the ligand, or it can be d pi or pi star. Like in case of CO, we have a pi star intibonding orbital, or it can be sigma star. Like in case of PR3 and NR3, where we have the sigma star symmetry, which is which is matching with a d pi. D pi is basically your dxy, dyz, and dzx, right? But N3 minus don't have such symmetry, which can form a pi bonding with metal d orbital. Okay, so what are the different kind of pi accepting ligand is there? It can be d pi p pi, d pi d pi, d pi pi star, and d pi sigma star. So d pi p pi is basically you can see like kind of your d pi p pi example. If you see, so you can go to the uh, but there also, like ethylene, if you take, there also that anti-bonding orbital will form a uh, uh, kind of like pi accepting. D pi p pi with this like simple. What is the example of halide donor or NH3, where we have d pi p pi? Basically d pi pi star is basically like CO Cn minus and CuCn minus and C2 CH2 CH2. What is d pi and sigma star is basically PR3, where sigma star orbital of PR3 has matching symmetry with d pi. Okay, so now I think the correct answer is uh, just delete these things. The correct answer is N3 minus, which is not a pi acceptor ligand. Now, is it clear? So first thing is that there should be a matching symmetry pi orbital present on the ligand. Okay, then you have to find out like what are the different kind of pi accepting. And there are few only pi accepting ligand like CO, Cn minus, PPS3, like PR3, basically, which has kind of pi orbital present. If you have any other doubt, you can ask. So for the pi setting, they should have some empty pi orbital where metal can donate the electron density. If you have any question, you can ask me. Otherwise, I will go to the next question. Any other question? No, I can go to you. The rate of exchange of cyanide ligand in the complex NiCN4 2 minus, MnCN6 3 minus, and CrCN6 3 minus by 4Cl follow the order. Can anyone tell what is the answer for question number 6? Okay, how to identify pi acceptor or pi donor? So it is very simple. I think I have to explain you more. Pi acceptor is basically they should have that empty pi orbital which is higher than the T2G orbital. But pi donor is basically they should have filled p orbital. Like you have NH3, there is lone pair, so that can be a pi donor. You have like all the lower series like halide is basically a pi donor because they have filled p orbital. Okay, so can anyone guess what is the question number answer for question number 6? Anyone has any idea? They can just write in chat box. Rajendra sir, is it clear how to identify pi acceptor and pi donor ligands? Just if you can write in chat box. Yeah. So can you write and answer for this question number 6? Any idea? What should be the rate of exchange for cyanide ligand in complex? One basically NiCN4 2 minus, MnCN6 3 minus, and CrCN6 3 minus. By 4Cl, follow the order. Any idea? We'll wait for a few more seconds. You can just uh, think and let me know what will be the answer for this question. No idea? Okay, so let me tell you. So first thing, this is somewhat related to the inert and Levy complexes. So now there is four term total. First one is the thermodynamic, thermodynamic, So in this we have two things, whether your complex is stable or unstable. We have kinetic term, which is of two type, whether it is labile or it is inert. So if I ask what is the definition for this labile and inert? Okay, so labile means your reaction takes place within 1 minute at RT, and concentration if you will take 0.1 molar. Inert means basically it will take more than 1 minute. So this is the definition for the kinetic term, basically whether it is reacting or it is not. But thermodynamic term is different, like whether the complex is stable or unstable. So basically it is determined by the formation constant K. Higher the formation constant, more stable the compound. So, but is there any relation with the these four terms? So there is no relation between the stable and level. So a compound may be stable, it may be level. It doesn't mean stable means it will be inert, it will not react. A stable compound can also be inert. That is the already example professor has told. Okay. Now coming to the question. Rate of exchange of cyanide ligand in complexes CNI CN4 2 minus, Mn CN6 3 minus, and CR6. So first thing, this is the square planar complex. This is octahedral and this is Mn3 plus. Mn3 plus means basically your D4. And this is chromium 3 plus. Chromium 3 plus is basically D3. Right? So now if I go to the, sorry, where is that? Okay. Okay. So now if you want to answer this question, so first thing you know that your square planar complexes are generally labile. Okay. Second thing, we know that if you have configuration, the rate of single Mn equals D4 and CR, this is D3. Okay, yeah, fine. So second thing is that if we go in octahedral, so basically we see the electronic configuration. If it is a stable electronic configuration, means it will be the inert. So if we see that Cr3 plus is basically your D3. D3 if we see, basically just see the concept of your 1, 2, 3, 4, 5. Okay, so basically it will be the D2 sp3 from here. Yes, 1 minute. It will be the D2 sp3. Basically, that this is the electron from the uh, ligand. Now we see the configuration D3. It is very symmetric and stable. So that's why it will be the inert. Now we see configuration that are the 3 orbital is basically differ from this. So that will be the level. Your Mn3 plus is basically more labile compared to the D3 system because it will give the stable complex. That's how valence bond theory. And square planar complexes are generally labile. So if we see like um, from rhodium 1, iridium 1, nickel 2 plus, palladium 2 plus, platinum 2 plus, gold 3 plus are labile complexes. The correct answer is the B. So these two concepts is there. First, square pyramidal complexes are generally more labile compared to the octahedral complexes. Second is that stable configuration. So this D3 is the stable configuration compared to the D4. Okay, so it will be. Otherwise, one more thing is that you have to just take the help of uh, crystal ligand field theory, and you calculate what is the CFSE difference between the uh, like basically your intermediate and the octahedral. So if we are seeing more loss in CFSE, basically that will not that will not be favored. Means it will be generally if there is a less change in CFSE, that will be favored. So if you calculate, basically you will see that this is the positive, means no loss for the this Mn3 plus, but there will be a loss in the uh, this chromium 3 plus basically. Okay, so that's how we can see that answer. Question: for a pi donor ligand delta 0 considered between. Can anyone write in chat box what will be the delta, like delta 0 considered between for a pi donor ligand? We'll wait for 1 minute. Rajendra sir or Rupali ma'am, any idea for a pi donor ligand? What will be the delta 0 will be basically considered between T2G to EG or T2G to EG star, T2G star to EG star, and T2G star to EG star. Any guesses? Can anyone guess for this question number 7? B T2G to EG star. That is not the correct answer. The T2G to EG star for a pi donor ligand. T2G to EG, that is also not correct. Okay, so let me explain you first. So what Rajendra sir is saying is basically he is taking the normal crystal field theory. So we have like splitting. We have this T2G, we have EG, and this is delta 0, right? So this said that crystal field theory. Now what Rupali ma'am is saying is basically she is considering the LFT for the sigma bonding. So once you take the sigma bonding, basically we have T2G non-bonding orbital, and then we have Eg star, right? And this is your delta zero. This is the sigma complexes considering the ligand field theory. But now once we have pi donor ligand, what changes happen? So just let me draw the uh, uh, ar- uh, uh, orbital molecular orbital diagram and then explain you. So first, this is your metal and this is your ligand. Now metal has T2G. So this is the metal ligand sigma complex I'm writing. Okay. So we have T2G here. Sorry. And then we have Eg star here. And after that down orbital also there. On ligand we have basically your T2G orbital. Already told you, like if we take the like irreducible representation for ligand, it will have T1G, T2G, T1U, T2U. But EG, T1U is already involved in the sigma bonding, so only T2G orbital has symmetry, which is has on the metal. Now it will form a bonding and it will form as anti-bonding. Now this is your T2G and this is your T2G star. Now we have here Eg star. So this is your first delta 0. This is your delta 0 dash for the pi bonding electron. So your delta 0 is basically considered between T2G star to Eg star for pi donor ligand. Okay, and it is less than sigma complex. It be considered only sigma bonding. So the correct answer is that D. Okay, I think now it will be clear. Can you just write in chat box that it is clear now for sigma donor delta 0 will be considered between T2G star to EG star. Can you confirm in chat box that you got the point? Is it clear? Okay. So now the next question is the correct order for the rate of exchange of water molecule between the coordination sphere and the bulk each. Option A is chromium, aluminum 3 plus, chromium 2 plus, nickel 2 plus, chromium 3 plus, aluminum 3 plus, nickel 2 plus, chromium 2 plus, chromium 3 plus, nickel 2 plus, chromium 2 plus, aluminum 3 plus, or chromium 3 plus, chromium 2 plus, aluminum 3 plus, nickel 2 plus. Can anyone guess? Okay, Rupali ma'am is saying no idea, no problem. Okay. So he's saying that first chromium 3 plus and then chromium 2 plus aluminum 3 plus, and that is not the correct answer. Can you tell me what is the reason behind you are saying that this is the D is the correct answer? Rajendra sir, do you know like kinetics of octahedral substitution, basically water exchange, and what are the class 1, class 2, class 3, class 4 elements? Similar, smaller ionic radii, so slower rotation. That's correct. It's correct. It's okay. So that is not the only that is the one of the criteria. There is charge also, there is ionic radii also, and there is a CFSE also. There is a three things which together give basically four types of the metal. So what is class 1 metal? So first I will just 1 minute. I will write kinetics of octahedral substitution. In that basically we are dealing about the water exchange. So basically class 1 class 1 is the uh, metal which has extremely fast kinetics, extremely fast water exchange. So basically their rate will be 10 to the power 8 second inverse. It is very high, 10 to the power 8. So what kind of metal is there? Basically we have the alkali metal, alkali metal, alkali metal, and alkaline metal, alkaline metal. With that we have group 12 like 3D element except Jadian 2 plus. Okay, and sorry, group 12 element, not this group 12 element except zinc 2 plus, and we have chromium 2 and copper 2. Now you will ask the question, why chromium 2 and copper 2? That answer will come from the John Taylor distortion. Okay, if you consider John Taylor distortion, so basically 4 will be of the different radii and 2 will be on the different radii. So these two water can be easily exchanged with them. That's why their rate is extremely high. So first chromium 2 plus will be the highest in this class 1 material. What is the class 2 material? Class 2 have like water exchanges. Water exchanges fast. This is the class 2 material, and their rate will be 10 to the power 5 to 10 to the power 8 second inverse. Now, what kind of material basically we have? So we have your first transition metal, first transition metal in +2 oxidation state, except what we have in the previous chromium and copper. These two are not part of, because they have already come into the class 1. So their LSFE, LFSC are relatively small. Third one is class 3. Class 3, their water is the water exchange water exchange is relatively slow, relatively slow compared to the class 2. So in this, what is the like generally rate constant? 1 into 10 to the power 4 second, where your basically what kind of material is come? Like basically most of the uh, like transition metal in plus 3 oxidation state from the and basically in this, one more thing is that stabilized to some extent by LFSE. That is the most important thing. And we have beryllium 2 plus, aluminium 3 plus, and vanadium 2 plus, like that. Okay. Class 4 is basically they have water exchange is very low. They have in my 10 to the power minus 1 to 10 to the power minus 9 second inverse. And in this, what is basically come? The inert complexes will come. So I have already discussed chromium 3 plus will be the inert in octahedral. Why? Because if we see that there is a loss of CFSE, that is the one reason. If we consider that ligand field theory, second thing, if we consider the valence bond theory, so this is most symmetric electronic configuration. That is the other thing. Now if we see, first one is the chromium, second it will come your first transition metal, that is nickel. From third they have taken the aluminium, and from fourth they have taken chromium. So the correct answer is the B. Now Rajendra and Rupali ma'am, is it clear? The correct order for rate of exchange of water molecule between the coordination sphere and the bulk. So how people has described the class 1, class 2 and class 3 and class 4? Okay, great. I will go to the next question now. Choose the incorrect option. Increasing ligand field stabilization energy minimize the inertness. Complex react rapidly indicate it is inert in nature. Plus 2 metal ions generally labile in nature. Strong field D6 octahedral complexes are inert in nature. So which is your like uh, choose the incorrect option. Can anyone tell? C plus 2 metal generally labile in nature. We have to choose the incorrect option. Incorrect option. We have to choose the incorrect option. The complex react rapidly indicate that. Okay. Okay. So saying the answer. Okay. So let's see what. So generally we say that plus 2 ion D metal are moderately labile, particularly D10. Like that is the one. This is the plus 2. This is correct. Second thing is a strong field D6 complex are inert in nature. That is the uh, region here that is strong field D3 and D6 octahedral are inert because there is the most symmetric structure. This is the for T2G3, and if we take T2G6, basically it will be like this. So they will be inert. They have no anti-orbit. Complex. This increasing the ligand field stabilization energy basically improve the inertness, but this is saying the minimize the inertness. So that is one incorrect option. Second also looks like that complex react rapidly indicate that it is inert in nature. That is also incorrect. So I think this should be options, and these two are the correct option for the question number 9. Okay, because complex which react rapidly indicate that it is inert in the nature, which is incorrect because it will be labile in nature. Okay, so the correct answer is A and B both. Okay, clear? Can I go to the next question? Okay. The rate of exchange of O2 present in coordination sphere by 18OH2 of copper, manganese, iron, nickel follow in order. Can anyone guess what is the rate of exchange of OH2 present in coordination sphere by 18OH2 of copper? Can anyone guess what is the rate of exchange of water? Correct option is B. First, fourth, third, second. Rajendra sir is saying B. Can you write what is the logic? What is the reason? In what direction you are thinking? Both the answer is incorrect. B and C. Can you people write in chat box like what is the line of thought? Like how you are thinking that this will be the answer? Is there any like a reason how you people are thinking? Can you people write just one line, like how you are thinking that uh, whether A, B, C, D, which is the correct, what is the line of thought? How you people are thinking that this will be according to me, this should be the correct answer. The smaller the radii, slower the rate. Ma'am, I already told you, like that is the not the, that is the one of the criteria. Okay. Now let me tell you what is the reason behind this. So first thing is that, can I ask you people what is the structure for this? What is the geometry for this CuOH26? Anyone? That that is not correct, because that is not the correct, like CuOH26 is not octahedral. It's a distorted octahedral. Okay, so here John Taylor distortion is there. Okay, John Taylor distortion, and because of that only, this is the most labile. And I told you that it is a class one uh, metal, like metal complexes, where the rate of exchange is 10 to the power 8 second inverse. So first CuH2O6 will be the first, it will come into the first. Okay. Now who will be the last? Last will be the most symmetric structure, that is T8, like nickel, because you have like see 1, 2, 3, 4, 5, 6, 7, 8. Most symmetric structure, most stable. So it has least towards the reactivity. This you can tell by valence bond theory also. So force will be last. So this will be the correct answer. In between, if you wanted to know that whether Mn and Fe which one will come, so you have to consider the loss of CFSE value. So how you will consider? You have to write the system. You have to write this is the high spin complex. Now if we have coordination number 5 and you have coordination number 7, okay, what is the loss in CFSE for D5? So if we go to coordination number 5, it will be 0. If you go to the coordination number 7 also, it will be 0. For what is for D6? For D6, we have plus 0.7 and we have 1.28. Now here in this case, there is not there is no loss in CFSE. That's why D6 will be more labile compared to the D5. That you have to take the account of the ligand field theory and consider that from octahedral, if we go to the square pyramidal, from octahedral, if we go to the coordination number 7, so coordination 7 number 7, this will be not the, it will not go in water exchange reaction. Basically, it will go through the, so first order, so it will go through the coordination number 5. We have to see that whether it is loss of CFSE. If it is negative, it is leads to the stability and it will inert. And if it is like plus in or 0, it is basically towards the level. So that's the way you have to see the answer, like find out the what is the correct answer for this question. Okay. Next question is for a, this is you have to write pi acceptor. For a pi acceptor ligand, delta 0 considered between. Can anyone tell what is the answer? T2G to EG, T2G to EG star, T2G star to EG, or T2G star to EG star. Okay, anyone else? Can anyone else guess what is the answer for this question number? Rajendra, so that is incorrect. That is for the pi donor, not pi acceptor. For pi donor only we have T2G star and EG star. But if we draw this structure for the molecular orbital diagram for the pi acceptor ligand, then the answer will be different. Okay, so let me draw and tell you. So first we will write metal ligand sigma complex. What are the energy level? We have that is also incorrect. So once we go to the ligand field theory, that is not Eg, it is always Eg star. We have metal ligand sigma complex, which is T2G there and Eg star. In between these two is the delta zero. This is the metal to ligand sigma complex. Only we are considering sigma bonding. So can I ask one question? Like, have you gone through the ML6 MODEN diagram? ML6 MO diagram for the where we have six sigma bonding only. And just write in chat box whether you have gone. Otherwise, I will just plot for first sigma bonding and then go to the pi one. Rajendra sir, have you gone through the ML6 basically like octahedral complexes, how the molecular orbital looks like? So just give me a second. I will just insert one new slide and then we'll tell you. Okay. So first we have this here 3D metal, which are of two types. EG we have, yeah, that's it. EG we have and T2G we have. Then we have 4S, which is of symmetry A1G. Okay. Then we have 4P, which is of symmetry T1. Now this is the all the metal orbital present. This is the metal. Now here we have ligand, which once we do we find out the irreducible representation. These are the orbital it will come A1G, EG, T1U. This is the six orbital. Uh, this is doubly generated. This is triply generated. This is singly generated. So A1G, EG, and T1. Now A1G will basically interact with your this A1G orbital of ligand. It will form the A1G bonding orbital, and then you have A1G star as an anti-bonding orbital. Okay. Now we have here what we have EG. It will form you the EG bonding orbital, and it will form the EG star. This is EG. This is EG star antibonding. Then we have T1U. It will form a T1U bonding orbital, and it will form, sorry, this I will just, okay, it will form T1U star as an antibody. Now we feel here we have 6 electron, right? And metal have, suppose if we are considering D1, so metal has 1 electron here. Okay, now we feel the electron 6, sorry, total we have 12, right? 12 electron, because 6 ligand, 12 electron. So 2, 4, 6, 8, 10, 12, because this is 2 Eg orbital. So 12. Now metal has, now this is the non-bonding orbital, T2G. T2G. It has 1 electron. And this is your delta 0. So delta 0 in sigma complex is what? T2G2 Eg star. That's how I always write, like I am just drawing this one, not the whole one, for the explaining the things. Okay. So we have A1G, T1U, EG, T2G, EG star, A1G star, and T1 star. So T2G to EG star is your delta. Now come to here. Now you have your pi acceptor ligand. So pi acceptor is basically what? They have the pi star anti-bonding orbital. Anti-bonding orbital. Now they are generally empty. They are empty, they will be higher in energy. So it will be somewhere here. 3 orbital is there. Now, once it will interact, it will form bonding orbital and it will form anti-bonding orbital. Right? So this is your T2G and this is your T2G star. Now here is your EG star. So this is your delta 0. Now delta 0 is defined by T2G to EG star. For this case also, the correct option is B. Rajendra sir, now is it clear? Like everything, the molecular orbital diagram or metal to ligand, if we are considering only sigma bonding, once we are considering the pi bonding for the pi accepting and uh, pi donor, I basically that I have already told you. Is it clear? Okay. If you have any other question, you can ask me. And you can refer to the sir's lecture also, where he has already like discussed how like irreducible representation and other things will come. Okay, so I think this is the done. In next class I will be basically completely, that focus will be on the uh, reaction mechanism. So this is reaction mechanism 3, 4, 5, 6, 5 up to 5. What are the different kind of thing? We will discuss the basic hydrolysis. Then we will discuss the associative, dissociative, interchange, associative, interchange, dissociative. What are the critical things in the next class, like on Tuesday? So this is, I have already like take the pictures of those things. So I will upload on the what is called on the whatever the Excel sheet that has shared, that has been shared with me, and you can go ahead. So these are the things I have already told you, like what is the ML6 and when we have pi orbital, what will be, so why it is lower in energy, why they are being filled ligand the pi donor, because basically it will that gap will be, previously this is the delta 0, now this is the delta 0, so basically this will be the lesser than the this one. Okay. So if we are going to the pi acceptor ligand, this is the molecular orbital cu. So this you can see that how sigma bond and pi bond will form. So this is the these things, and summary professor has already discussed, and then reaction mechanism, what is the inert label, those things I have already first uh, uh, accumulate this. So in next week, the all the problem solving session is basically focused on the reaction mechanism and the little bit about the biological inorganic chemistry. So we will discuss some complexes which are basically present in the human body are basically uh, blood. This whatever this hemoglobin and other etc. Zinc, sodium complexes, all those things we will discuss. Okay. With that, if you have any other question, you can ask. Otherwise, I will just sign out this. Okay. Anyone has any other question? Okay. Yeah. Thank you. So I will just stop the recording now.